All right, welcome everyone to this Black Belt session. Today we have Amin and Roberto from Docker. Amin has been here for over a year. She's a data engineer on the data team at Docker. And Roberto has been here for a long, long time. He says he's been here before Docker was cool. So more than 5 years. They're going to talk about categorizing Docker Hub public images with machine learning. So that sounds very exciting. And so please give it up for Amin and Roberto. Thank you.
Thanks, Tibor. Can everyone hear me? Okay, awesome. Well, thank you for being here. You lasted all of DockerCon, and just bear with us. Hopefully it'll be smooth sailing, minus my bad luck with the demo yesterday. So we are the data team at Docker, and we build end-to-end end-to-end data pipelines for the entire company, basically surfacing analytics for various functional groups within the company. And so most of our time is basically spent on delivering analytics, and we don't really get to spend too much time on data science. So this project was essentially for ourselves to be able to develop an environment where we can operate in and to have our own machine learning workloads, but then also provide a way for our customers and for the community at large to be able to do the same. So today we'll go over the problem that we wanted to solve with machine learning, kind of dive into the architecture and the developer workflow and what it looks like, while highlighting some of the key Docker Enterprise features that make this a production-ready stack. And finally, we'll end with some of the challenges and what we intend to do as next steps. So now, how many of you have ever pushed an image to Docker, just a Docker push? Everyone. So whenever you push an image, it also makes its way to hub.docker.com. Is this flickering or is it just me? Okay. So if anyone's ever pushed a Docker Hub, which I think all of you have, so the image ends up on, your repo ends up on hub.docker.com as well. But the way it operates is that whenever you need to download something, whenever you're like doing a Docker Hub pull, you have some sort of a prior context to that repo. Someone is asking you to download it from there. And similarly, when you're pushing to Hub, your repo's discoverability pretty much primarily depends on the kind of effort that you take in promoting it. How we envision Hub to look like is more of now a marketplace for repositories, such that you're able to, perhaps, let's say, if you're looking for a monitoring solution, when you go to Hub, you should be able to see what else are people, in the community installing, what's missing in your stack. If monitoring solution A is there, well, what's B, C, and D? But in order to do that, we need to know what exactly is in those repositories and what's in them, how similar they are to one another. And that's where the problem occurs. We have over 4.6 million repositories on Hub, and none of them are categorized, which means we don't really know what exactly is on Hub. So in order to do so, we thought as a first step, let's perhaps look at the descriptions that users provide us with on the repositories and use those descriptions to determine labels that apply to them. And that would hopefully be a stepping stone for perhaps a categorized search or even something like a machine learning recommendation engine. So now while we feel that we need something like that, the first step to that is data science. So now that we have a solution in mind, we realize that maintaining and building a machine learning pipeline in production is not a very easy task. So how can we sort of make it easier for data scientists and data engineers to deploy end-to-end machine learning pipelines in production, while also have CI/CD in place inherently to make it into a proper developer ecosystem? So how can we automate these pipelines? Now today we'll cover how we implemented Kubeflow on Docker Enterprise to deliver a trained model and to train and deliver an end-to-end machine learning model. Now, like any developer ecosystem or process or team, there are always various stakeholders, and there can be inherent tensions within that particular environment. I'll let Roberto take over now to talk about how Kubeflow helps address those tensions and reduces bridges and gaps that currently exist.
Thank you very much, Aman, and thanks everyone for being here with us today. So now we are going to talk about the personas. And what we are going to do here, the goal that we have here today is to go through the journey of getting this model deployed on a Docker Enterprise environment. And how many of you are DevOps engineers? And how many of you are data engineers? And how many of you are data scientists? Okay, awesome. So yeah, so usually we have these three well-defined personas when we want to do a project like this. And the DevOps engineers usually provide the infrastructure and maintain the infrastructure with security and all the services required to run this stack. We have the data engineers providing the machine learning pipelines, the data pipelines and maintaining these pipelines with new data sources. And the data scientists, they develop models and reports and answer business questions based on this data that's collected by the data engineers. So this is the status quo, but what we are seeing now is a trend where data engineers and data scientists are trying to have more autonomy to get this development process speed up and to have more end-to-end ownership. And as a result of this trend, we see that we are seeing an emergence of a new persona that strives for this culture of end-to-end ownership and innovation. And we are calling here data ops engineers. And this allows them to deploy these models, do them in a faster pace, and get to test and evolve the model over time. In this context, we have Kubeflow that helps us by handling most of the heavy lifting of deploying these machine learning models. And how many of you have tried Kubeflow before? Awesome. So yeah, so Kubeflow facilitates the deployment of these machine learning workflows on top of Kubernetes, and it leverages lots of tools developed by the community, and we are going to talk about each one of them in the next slide. So this is the architecture that we have. We have all these blue boxes, the light blue boxes, deployed out of the box when you deploy Kubeflow. So we have Ambassador, which is an API gateway to service your model. You have Argo, which is a CI/CD workflow automation tool. We have Jupyter Hub, which is a multi-user server for Jupyter notebooks. We have TensorHub, which is a registry for reusable machine learning modules. And we have Katip, which is a hyperparameter tuning on top of Kubernetes. And in order to serve your model, you need to choose one of the serving components available. You can use TensorFlow serving or Seldon-Core. In our case, we chose Seldon-Core because it has out of the box some monitoring for your machine learning models and also some wrappers to wrap your model once you develop the model, either like in Python, in R, in Java, in Node.js. So we chose to use this one. And as you can see here, this stack can be either deployed on Docker for Desktop in your local machine, and that's the environment of choice that we use at Docker. And we can also run this on a Docker Enterprise running in the cloud. In our case, we chose to deploy this on AWS. Now going deep into the architecture of Seldon-Core. So once we submit a job against the Kubernetes cluster, we talked to the Kubernetes API. We use these components that belongs to the Seldon-Core architecture. One is the operator that takes the description of your machine learning deployment resource. And in this case, we are using a custom resource, CRD, which is called Seldon Deployment. And we takes this description and then the operator deploys it on top of Kubernetes. And then the service orchestrator takes this and this deployed model and manage the flow of the data between the different endpoint or the different backend services. So in this case, you can see you can have multiple models running at the same time. You can deploy different versions, and all of this is exposed through this Ambassador API gateway that allows you to automatically create new routes as you deploy new models. And as part of this configuration, you can choose if you want to expose your API either through REST or gRPC. And it's very simple to do this change. It's just a configuration change, and we're going to take a look at that later when we do the demo. So now let's talk about the development process. So here we started from a local machine running Docker for Desktop, and we develop our model using this Jupyter notebook. And once we are satisfied with the model, we are going to push this model or this source code to GitHub. And as you can see here, we are using S3 to pull this data and try this model locally. And then we push to GitHub. And once you have this on GitHub, this triggers the CI/CD pipeline. We are using Argo to go through the CI/CD process. And we also use S3 to upload the artifacts of each step of this workflow. So you can do some analysis later. And one of the last stages is to build and upload the image to the registry. In our case, we are uploading this to Docker Trusted Registry. And once the image lands there, it will be automatically scanned and automatically signed as part of the workflow. So here is like we are using a content trust feature. You can sign your image with this Docker Trust command line, and we are doing that automatically. Then with the images are scanned, and once we have this image scanned, we have a promotion policy in place. So in this case here, we have like only image that will be promoted, only image that meet this requirement in terms of critical vulnerabilities equals to 0 will be promoted. So this is one example of the policies that we put in place for this example for this project. So now that we have highlighted some of the features that we used from the Docker Enterprise platform, and these are mostly related to the Docker supply chain control that's leveraged by the DTR system or platform. And now that we have this infrastructure in place to deploy these machine learning models in this production-ready environment, I'm going to let Aman to take over to explain in details how we develop a machine learning model from Jupyter Notebook.
Okay. So we've basically condensed typical machine learning or data science stages into about 5 steps. Now they encapsulate a lot of the steps that already exist. So the first step you want to start off is with your data. In our case, it's hub data, for instance. And from your data collection stage, you want to be able to do some form of exploratory data analysis or experimentation. Perhaps look at the spread of the categories that exist in your data, look at outliers, perhaps even look deep into the data for correlations that you might not have thought about. And then you want to be able to clean your data. So let's say it could be stop word removal or looking at stuff like maybe ASCII, non-ASCII characters, you could remove those, that sort of stuff. But then you also want to be able to transform your data in a form that is suitable to your classifier or your neural network. So let's say if you have descriptions in words, you should be able to transform them into matrices of numbers that would work well with your machine learning algorithm. And then finally, you have the model building phase where you divide your data set into training and testing, and then you train your machine learning algorithm on the training data and then verify it and test it, predict using the testing data that you have. And then you could use grid search or other means to further tune your model and improve your parameters to get better predictive capabilities. And then finally, you want to be able to deploy that model in production in a manner that's scalable, while also be able to monitor that and log it at scale. Now, for us, that would mean that we need to expose our model as an API so that the hub team can maybe send descriptions over to us and we can respond with the categories that we feel, that our algorithm feels are relevant. Now, while the purpose of this talk is not to look into the machine learning or the data science in particular, we just thought we'd have a little bit of fun and dive into a Jupyter Notebook. Hopefully that will work. Load it. Awesome. Looks like I'm not carrying my bad luck from yesterday. So here's a Jupyter Notebook that we have, and this could potentially be running on Kubeflow and Docker for Mac, or you could be running it from your Docker Enterprise server. If I'm running it over there, then it allows me to share my models with Roberto easily and helps with code collaboration. Now, first off, we imported Keras. Now, Keras is a higher level API that runs on top of TensorFlow, which is a popular machine learning framework. And then we also import Pandas. Pandas is a popular Python library that helps us deal with data frames. So once we have these, and you can also see Keras is using TensorFlow as the backend, we import the data into a Pandas data frame. Now the data that we have right now, so the way we got it is we got some data from GitHub topics. So GitHub topics GitHub started this initiative where they have topics for different repos. And we looked at a bunch of categories that we felt were relevant to our use case, got those from GitHub, got a bunch of categories from stackshare.io, joined that data with the hub data that we have currently. Now, because we needed predefined categories for hub data that we had to do this because we wanted to have more of a supervised learning model. This is just like a small dump of the data where we've done some minor pre-processing just for the sake of saving time today. But you can see the category 1, 2, and 3 for each repository have been concatenated into a separate column called labels. So and we're working with the full descriptions for this part. So these are just long descriptions that you normally see on a hub repo. Scroll further down a bit. Thank you. Now, these are the categories that we've decided to go with. There are about 250 categories that we were able to collect, but we decided to prune them down to about 82 as they exist right now. And further down, sorry, thank you. And then you can do, some kind of, why isn't my chart printed? Should have been a chart there. I thought you ran the notebook. Can you just open GitHub? It will be rendered there. It's all right, I can just skip it. So you can look at the spread of the categories. There was a chart here, I promised, that looked kind of nice with different colors and showed all the categories and their spread. And then what we do is we clean up the data set in a way that we clear the full descriptions, remove the stop words, remove the punctuations, and non-ASCII characters, drop duplicates from the data frame. And then we come to a process where we hot encode the data in the pandas data frame. So by that, I mean for every category, I've added a column to the pandas data frame such that if, let's say it's a DevOps repo, then DevOps would have a 1 underneath that particular repo. So we one hot encode the data set, so now it's like, 85 columns by the number of rows that we have. Further down, Roberto. Thank you. So now we can also perhaps even look at word clouds of the data that we have. So for instance, here I have DevOps. So for all the descriptions that are tagged as DevOps, I just printed a word cloud for this. Now these are just fun examples. I'm sure I'm not a data scientist, but I've been having fun with this as well. So here's a word cloud. Now, as you can see, there's a lot of Docker and build and run in there. So then we realized, okay, we need to have our own list of stop words because the English language doesn't really know Docker. So we looked at the NLTK library and we downloaded their list of stop words, updated those with our context. So we added like Docker or like build, for instance, or image, just to kind of further improve our data set and our algorithms and reduce the vocabulary size. So once you do that, then we remove Docker, so you can print out the word cloud again, and now you have a few words that are probably more important to us for DevOps than other words. Further down, thank you. Now the part where you train and test, where you divide your data into training and testing. So we use the scikit-learn library, and that's a very popular data science library in Python. What we did was we split the data. So as you can see, we've set test size equal to 0.3, which basically means that 70% of our data is being used for training and 30% for testing. Shuffle the data so it's randomized. And we take the full descriptions and we tokenize them such that you have words instead of the full sentences. And we use a Keras tokenizer to do so. And after the tokenizer, we transform the data using a TF-IDF transformer. That's basically term frequency, inverse document frequency, which basically attributes a value to every word based on its importance to that particular description, as opposed to the rest of the documents in the corpus. So that's your X values, and then the Y values are all the one hot encoded labels. So for instance, so we've dropped everything else from the pandas data frame, except in leaving only the one hot encoded value. So all you see are ones and zeros in the pandas data frame. Once we've done that, we then use a sequential model with Keras to have with the two-layered neural network. With the first one, it relies on a ReLU activation. You could have also used TAN-H, for instance, and with an output layer, and an output layer with 82 neurons that is based on the number of categories that we have. And we used a binary cross entropy loss function with an Adam optimizer, which is a popular optimizer. And then once then you want to be able to fit and evaluate your model. For that, we used a batch size of 100 and 15 epochs. So once you have your score, then you can get your score as an evaluation for your model. So you have your loss and your accuracy that we printed out here, and then you can also see that as a graph. So 0.98 accuracy, that's the binary accuracy that we put in the function, and 0.1 as the loss. Sorry, further down. Yep, thank you. And then just the last part, you can just scroll over to the end. Okay, so then we've made a predict labels function that basically takes in a description and spits out categories that apply to it. Now, the way the model predictor works, it gives probabilities for each word. So as a potential category for that description. So we've set a threshold of 0.4 because we wanted to see more categories. But if you want your model to be more precise, you could have like a higher number. So let's say 0.5 or 0.6 as the probability of that word. Because we don't really care as much about precision right now. So that's why we decided to pick 0.4. So given a description for here, for instance, that's a description, I think, of Jenkins that you put in and it spits out categories. So for example, DevOps, or build, test, deploy. Back to the slides. Thank you. So now it's important to realize that we did all of that within Kubeflow. And Kubeflow, the way it provides, it operates on three principles of scalability, portability, and composability. So this is a diagram that David and Michelle from Kubeflow normally use. I borrowed it from them, gave it Docker colors, so I'm just attributing their ownership to this diagram. So on the left are all the different steps that I had previously condensed into 5 stages. But the fact that Kubeflow allows me to have an environment for each of my stages from my experimentation phase through my training to eventual deployment on the cloud makes it easy to be able to test my model end to end within each stage from my laptop and eventually to the cloud. And that's where Kubeflow becomes so powerful. And with scalability, we don't only mean being able to add more nodes. It also has to deal with the fact that we're able to run more experiments simultaneously and we're able to provide an entire stack throughout the various stages of the life cycle. And that's what it looks like. So now that I have my predict labels method, I have my model, I want to be able to deploy it in production. And I'll let Roberto guide a demo on how we decided to do that and implement the servicing of the model.
Thanks, Aman. All right, so now that we have this model in a Python notebook or Jupyter notebook, we're going to see how we take that from there and put it like in on Docker Enterprise. So the first part, it's very hard to see what's going on here. Okay, so what we did first was to break those steps down into smaller functions. So what we did here was to create one process data function or Python script that takes the input data from S3 and process using those steps that Aman showed before. And then the output is just the training and test data, CSV files, and the selected categories. And the other part is the training. So we are exposing these training parameters through this script, and we run the training here. So now that we have those steps segmented in these different scripts, we create an Argo workflow to try to automate this process of training. So all the steps here import the data from S3, process the data using those steps, train the data, and then build and push an image. And the last one is deploy your model. And you can customize all the parameters of this model training, like the loss function, the data about your bucket, S3 bucket. So everything here is customizable, and you can change it. And now let's take a look how it looks like from the Argo UI. So this is the Argo interface. So at glance, you can see how long it took to run this job. And this job was triggered when it was a commit against GitHub. So it took around 12 minutes. These are the parameters. So here's the registry. In our case, we use the DTR. So we're going to push this image against the DTR registry, the S3 bucket, the key for the data input, the Docker certificates to talk to the DTR instance and all the parameters related to the model itself. So here you can see how long it took to train, to process the data, to train, and you can access from this interface all the artifacts of each stage. So here you can download your model that was outputted as part of this training stage. You can do the same for the vectorized categories. And then we built the image, pushed to DTR, and the last stage was the deploy. And on the deploy stage, you can take a look at the description of this stage. It's just a Seldon deployment resource, which is a custom resource created by Seldon-Core. It's hard to see, but we are going to take a look at that now. So this is deployed. Now let's take a look at the cluster. So on the left side, I have a cluster on AWS running Docker Enterprise, and on the right side, I have my Docker desktop running Kubeflow as well. And I'm gonna see if I can take a look at the Seldon-Core resources. Are you guys able to read? Okay, so here we have 3 Seldon-Core deployments. Let's take a look at this one, the last one. So this is the description of the Seldon-Core deployment. So we have all of this. The important part that we should see is that the image used was an image that's hosted on the DTR registry from the prod namespace. So we built this image in a dev namespace, and then it was automatically promoted because it followed the requirement was met as part of the promotion policy. And you can see the number of replicas is 10. So if we want to change the number of replicas, we can do it from here.
Do it clear so people can see it.
Yep. So let's scale this down. And as you can see here, the configuration that we need to do to expose this endpoint as a REST is just to change the name here from REST to gRPC. And you can have your gRPC endpoint automatically exposed through Ambassador. So let's change it to 5, save. So now if we take a look at the number of pods running, we should have some pods being terminated. Yep. So we have some pods being terminated. And we should have 5 replicas running now. And we can see the same thing from our stack running locally. So this is running on my local machine with Kubeflow. We have the same stage. It took much longer to build the image because I think I didn't have cache locally, but it pushed and deployed locally on my machine. So you can do the same thing that you were doing, like when we were going through this Jupyter notebook. This was also running locally, but you can use the Docker Enterprise server to use your Jupyter notebook as well. So I think this is the main things that I would like to show. And let's go back to the slides.
The dashboards? Can you show the dashboards?
Oh yeah, sorry. We didn't test the model yet. So now let's take a look. Let's try the model out. So I'm going to submit a curl command against the Docker Enterprise endpoint. So you can see that it's v4, the latest version, and we are passing this Jenkins-like description. Let's see what it gives us. So it returned DevOps, build test, deploy, and continuous deployment. So it's working. Now let's try the old version that is also running here. Oh man, without the screen it's very hard to see.
It's okay, Roberto.
Yeah, it's very hard. So now we are using, we are sending this request against the older version of the API, and it returned application hosting web servers. And this was resemble a description of AJ proxy description. So now let's take a look at the dashboard. So this is the dashboard that Seldon-Core provides for you out of the box. So as you can see, we got some requests from this older version of the model, and if we submit again against the newer version, we should see some tick here. Yep. So from this dashboard, you can see all the models that you have deployed, and it will be automatically expanded as you create new models, and the APIs or the endpoints will be automatically created for you without you to create new routes and API endpoints. And you can also see this cluster-wide dashboard is also given by the Seldon-Core framework. So now let's go back to the slides. Okay, we're gonna hand it over to Aman to show how we would use this from the Docker Hub interface.
So this is basically a design mock that we have for what we envision for this to look like on Hub. So we basically have a repo owner, Mike. Mike has a repository, and he's able to click on the Add Label button over there, and that leads to this page that shows all of the categories. So now these categories should be potentially coming from our service. So once Mike decides which categories are relevant to his content, he can click on them. And what we want to do is also learn from this sort of behavior. So whenever someone selects the categories that they feel apply to their repo, we want to be able to get that information back, save it, and retrain our model. So then when Mike clicks on save, then those tags are now attached, or those categories are attached to his repo, and they'll make his repository more discoverable as well. So that's what we feel it should look like, but this is still a design mock. So today we talked about how we can develop an end-to-end machine learning pipeline on Docker Enterprise, and we also looked at the developer workflow for Docker for Desktop, and while also looking at how we can log the performance of our API and of our models as well. But this is primarily a stepping stone for future machine learning work and for Hub as well. We could perhaps even look at the Docker files and the compose files beyond just descriptions, because not everyone provides descriptions for their Hub content. So that would be something we were considering of doing. The other thing we were thinking of was, so Kubeflow project released Kubeflow pipelines last month. We haven't had a chance to kind of experiment with them, but they act as a wrapper on top of Argo. So that should further reduce the complexity of setting this up and ease the process, because as it acts as a wrapper on top.
Yeah, something that we haven't done yet as well is to use the canary deployments and A/B testing. And you can do that if we add Istio in conjunction with Seldon-Core. And you know what? I think we should open source this to them to try it out by themselves.
What do you guys think? Would you like this? I need more of an enthusiastic response.
Yeah, we need...
No, a little bit of an enthusiastic
You guys want it?
Yes, yes.
All right.
Okay, fine. I guess we could do it.
Let's do it. Okay. Yeah. All right. So as you guys can see here, you can try this end-to-end workflow for Docker for Desktop in Kubeflow. You can follow it. This is a step-by-step guide to get this done, and we are really happy to share this with you guys today. And in order to make this work, we had to make some contributions to the Kubeflow upstream project to add Docker for desktop support, and we also made a patch internally to make this work well. So thank you very much for joining us today, and I hope you guys enjoyed.
Thank you, Roberto. Thank you, Amin. If you have some questions, we have time for like 5 minutes of questions. If you want to ask them to the mic, please come up to the mic. No questions?
That works for me. Everyone wants to get done with DockerCon.
I do have a question.
You do have a question?
I saw the word Jenkin and not Jenkins. So does that mean there's like some normalization done for plurals and things like that?
So we use some form of lemmatization as well. So like you try to, so if it's plural Jenkins, it probably thought of it as a tool to turn that into Jenkins. But yes, that's something to think about though. So thanks, Tibor.
No worries. Any other questions? Once, twice? All right. Well, thank you very much. You can
Thank you, everyone.
give warm applause again.
Thank you for attending DockerCon.